Good afternoon, everybody, and can I have the welcome to EE 544? Can I have the overhead, please? Thank you very much. Okay, good afternoon, everybody, and welcome to EE 544 again. Let's wrap up the overview material today and get it over with. Last time we started talking about modulation, and we said that modulation is the process of imposing the modulating information. So I have this. This is a modem. This is a modem. This is what we refer to as what? The modulating signal. This one is the what? Is the carrier signal. And the carrier signal, by the way, is what? C of t equal to what? A cosine 2 pi fct plus what? Theta. This is what? The amplitude. This is the what? The frequency, the carrier frequency. And this is the what? The phase. The phase is a relative measure. Phase is measured in degrees or radians. The frequency is measured in hertz. And the amplitude, of course, is measured in volts or amps, depending on whether it's a voltage signal or current signal. Where do we get this F sub C from? Where is this F sub C coming from? Who assigns? That is assigned, again, as I told you last time, it is assigned by the FCC. The assignment, by the way, when they assign a band, the band is either a what? A licensed band or a what? A licensed band. And a licensed band means the operators in that. By the way, let me mention one thing here. FCC can also assign a licensed band to a specific company, to a specific provider. I'm not sure, did you get my point? Did you get what I'm trying to say? So, for example, it will assign a given band to what? To Verizon to operate in that location. That band is dedicated to what? To Verizon. Notice, by the way, if that is the case, then the interference is going to be managed by who? By Verizon, because nobody else is using that band. Nobody else is using that band. The band does not need to be provided only to a single what? It does not need to be licensed to a single what? To a single provider. You could have multiple providers, but they are using a what? A licensed band. Those users, by the way, we will refer to them shortly as primary users. Why do you call them primary users? Because they are the one who paid what? Who paid money to have the right to provide services in that band. Other types of users, we will call them what? Secondary users. Those secondary users will have what is known as what? Cognitive radios. Those are the ones that are going to what? To sense the spectrum. You know, let me ask a question. Is this crowded? About 60 to 70% of them, even though it's crowded, is not used. I wanted to understand what that means. What does that mean when I say it's not used? 60 to 70%. It's idle most of the time. I am allocating you the what? I'm allocating you the spectrum, but you are what? Idle most of the time. In cognitive radio, which I will show you shortly, the radios are what? Intelligent enough to sense whether what? Whether the primary users are using the spectrum or not. If the primary users are not using the spectrum, the secondary users can what? Can provide for what? Can provide their own services. But once the primary comes, think about it this way, when the primary comes online, the secondary users needs to what? Needs to stop. Clear? Needs to stop. We'll talk about that shortly. And again, as I told you last time, the band is divided into what? Into multiple regions, what is known as what? The tremendously low frequency, the extremely low frequency, and so on and so forth. All of these, the MF, HF, and so on and so forth. RF, when you talk about RF, it's usually anywhere between 10 kilohertz to what? 100 gigahertz. So RF, when you talk about RF, usually referred to as 10 kilohertz all the way to what? 100 gigahertz. Clear? 100 gigahertz. All of this range is regarded as what? Is regarded generically, we call it a what? We call it an RF. Clear? Okay. Now, the other types of bands that are given is what? Unlicensed band. Unlicensed band, think about it as what? Free. Think about it as what? A free spectrum, like the one that is used in what? In Wi-Fi. In Wi-Fi, for example, in Wi-Fi, we have what? We have the 2.4 gigahertz band. We have the what? 5.5 or 5.75 roughly gigahertz band. All of these are what? Are licensed. Now, I want you to understand one thing before we go into the details. Unlicensed means what? Means you are not going to pay the FCC license to operate. You can operate, but that does not mean that you are unregulated. Don't confuse the unlicensed with what? Unregulated. Regulated means what? They will put what? The FCC will put requirement for you to what? To operate in. Just because you are not paying, it does not mean that you can transmit as much power as possible. So they put limits, for example, on power, on the emission, on your emission mask. They will put even some restriction on the format of your signal. Original, for example, in Bluetooth or the original Wi-Fi, they use what is known as spread spectrum modulation techniques, either direct spectrum, a direct sequence, or what? Frequency hopping, to make sure what? To make sure that your power is spread over what? A wider. That's a good point to bring the power spectral density, because last time you told me you did not know what power spectral density means. Power spectral density. This we will denote it by what? S of F, units. Anybody? It's watts per what? Hertz. Another name for watts per hertz. Another unit equivalent to watts per hertz. Still waiting. Still waiting. It's taking too long. Watts per hertz is the same as what? Joule. Why? Why? 1 over hertz is what? A second. Watts second is joule, energy. Did you get this or not? But I don't want you to call it joule. I want you to get used to just say what? Watts per what? Per unit hertz. This is how what? How the power is distributed over the band. Let me see if you can help me here. How do I calculate the average power, total average power? By the way, why I talk about average? Why am I talking about average? I'm talking about average because the signal is what? The signal is random. The signal is random. I need to what? Average it over what? Over all possible time. Total average power, which is measured in what? What is it equal to? A total average power in X of t, for example, is what? What is Sx of f? Sx of f is the power spectral density of what? Of X of t. Is the power spectral density of X of t. Question, what is this? What am I measuring? Analytically, what am I finding? I am finding the area under what? Under the power spectral density. The area under the curve. I want you to see this. And I want you to see this. Answer me the following question. Is it possible both of these signals have the same power? But this one is spread around what? Along what? A wider bandwidth, which means it looks to the other devices operating in the alliances band, it looks like what? Noise, background noise. Is it the same power? It's the same power. The area under this is the same as underneath. But in here, most of the power is concentrated in a what? In a narrow band, small band, whereas this one is what? It's spread over what? A wider band. This is called what? Spread spectrum. Again, it could be what? DS. DS stands for what? Direct sequence. And FH stands for what? Frequency hopping. And I will show you those later on. I just brought it to your attention right now. Clear? So in some cases, for example, in the unlicensed band, for example, in the Bluetooth, or even the original Wi-Fi, FCC requires that what? That the signals be
The time is 14 o'clock.
Signal be spread so that it does not what? It does not have a severe effect on what? On the other users. Clear? On the other users. Currently, of course, the Wi-Fi uses technology called what? OFDM. OFDM stands for orthogonal frequency division multiplexing. We will study that shortly. Let's not worry about it right now. Clear? So all types of what? All types of regulations can be. But let's talk a little bit about power before we get back to the charts. I need to make sure you know how to calculate the power. Okay, a calculation of average power. Let's take any, first of all, give me the example, P average. Equation, sorry, not example. I said give me an example. Give me an equation. Limit as t approaches what? 1 over t, the integral, from what? 0 to t, or 0 to minus t, of what? X squared of t dt. I am averaging the power over what? I am averaging. Oh, what is this, by the way? Just this. Just this one. What is this one? Just this one. That's the energy. Are you following me or not? That's the energy. I'm dividing it by what? The duration. Yes? And I'm letting the duration approaches what? Approach infinity, because I'm averaging over what? Over a long period of time. Clear? Okay. If signal is periodic, like for example the carrier signal, what is the average? In other words, let's C of t equal to what? Equal to A cosine 2 pi FCT plus what? Theta. How do I calculate the power? Average power. First of all, what is the equation become? Will it still be here? This is a what? A periodic signal, which means what? The signal is going to what? Repeat itself. So the average power is the same as the power in what? In one cycle, which is what? 1 over t, integral from 0 to t. Question, does it have to be from 0 to t? Could it be minus t over 2 to t over 2? Important thing is that it's over what? One cycle. X squared of t dt. What is it here? In this case, it's what? 1 over t, 0 to t, a squared cosine square 2 pi fct plus what? Theta d what? dt. What is this? 1 over t, 0 to t, a squared times what? 1/2 plus 1/2 cosine 4 pi fct plus what? 2 theta dt. Are you following me or not? Okay, and that's equal. The first term, what is it equal to? It's what? dt is what? 0, a squared over 2 is constant. 0 to t, dt is what? Cancel with this, so you end up with what? A squared over what? 2. What is the second term equal to? 0. Why? Because I'm integrating over one period a cosine. A cosine, the average of cosine is what? 0. So I get a squared over 2 watts. Did you get this or not? Yes or no? This is called the average power. If somebody asks you, and we will see that in just shortly, if somebody asks you, what is the peak power? What is the peak power? A very important parameter. We'll talk about that shortly, not now. A very important RF parameter is called the what? Anybody? Bar? Anybody? Peak to what? Peak to average power. Clear? Peak to average power. Now, first of all, let me say it in words before I show it to you. If the peak to average power is what? High, what does that tell you about the amplitude? The amplitude is what? It's changing. Are you following me on that? It's changing. It's not constant. Did you understand what I just said or not? And if it is changing, the modulation technique is what we refer to as what? Non-constant envelope, which means what? We need to be careful in designing our power amplifier that it does not introduce what? It does not introduce linearity. Whoops, does not introduce non-linearity. Clear? Whereas if the peak average ratio, the peak power to average power ratio, by the way, sometimes they call it PPAR, peak power to average ratio. Bar is good enough. If it is what? Close to 1, yes? Close to 1. By close to 1, I mean what? A little bit higher. The peak power has to be greater than the average power. Then it means what? The modulation technique has a what? Relatively constant envelope, which means it allows us to use the power amplifier in an efficient way, which means what? Near saturation. Clear? I will show you that in just a second. But let me ask you a question here. How do I calculate the peak power? The peak power, you calculate it by looking at, by the way, which one is easier to calculate? The average power or the peak power? The average power is much easier to measure and much easier to calculate. The peak power, you need to see in a very small infinitesimal period, in a very small infinitesimal interval, sorry, what is the peak what? What is the peak amplitude? Are you following me or not? What is the peak amplitude? Clear? The peak power is what? Is the square of the amplitude. In other words, there is no 1/2 because it's not cosine. You are just taking the what? The peak value. In other words, look how I define the peak power. The peak power. No ratio, sorry. Maximum. I want you to see the equation. What is this? When I say maximum absolute value of C of t square. Yes? What is it? Why do I say absolute? Why do I say absolute? It doesn't matter if the amplitude is what? Positive or what? Negative. Because when you calculate the power, you are going to what? Square it. Are you following or not? It's square. There is no divided by 2. This is not average. We are not averaging. We are looking at the waveform for a very what? A very small interval where the peak, where the amplitude is what? It's peak. Did you get this or not? What is it here in the case of the sinusoid? In the case of a single sinusoid, in the case. The peak power is what? As opposed to what? The average power is how much? A square over 2, which means what? We say the power is what? 10 log, again, it's in dB, 10 log A square over what? Which is what? 3 dB. Clear? Clear? Okay. We will talk, by the way, when will the power be equal to 1? When will the power be equal to 1? When the waveform is what? Constant. The amplitude is what? It's constant. Are you following me or not? Clear? Okay. We'll talk about that later on. Now, I want you also to see if you are familiar with this. Suppose asides. Suppose I have 2 sources. This is one source, plus, minus, voltage source, and let's call this one A, cosine, 2 pi. Let me ask you a question before that. Let me ask you a question. Does it matter if I change F sub C? Will the power change? This F sub C, if I change different F sub C, will power change? No, it will not. But the frequency, oh, but how about the phase? If I change the phase, will it change? No, it will not change. You follow me or not? The power is strictly a what? A function of the amplitude. You increase the amplitude, the power will what? Increase. Do you decrease the amplitude, the power will what? Will decrease. The frequency, whether FC is 1 megahertz or what? 10 megahertz, the power will be the same. Clear? Same thing with the phase. Now let's assume that I have two sources, A cosine 2 pi f1t, and this one is B cosine 2 pi f2t. And let's assume these two sources are uncorrelated. What does uncorrelated means? Anybody? Anybody? You take this if you take class in probability. Uncorrelated means what? There is no dependency, linear dependency between them. Clear? Notice, by the way, if they happen to be what? Noise sources, we will see later on when we get to the noise. If they are uncorrelated, then they also must be what? Independent, assuming, of course, that they are Gaussian. Clear? Don't worry about that right now. Assume they are uncorrelated. Uncorrelated means what? They have nothing common between them. Clear? What is the total average power? How would you calculate the total average power? Still waiting. Still waiting. Did you get it or not? The total average power is the sum of the average powers. Notice, by the way, in all of this, in reality, if I want to be precise, I need to divide by what? By R, the load. Did you understand that or not? But I'm assuming that I am measuring the power on a what? On a per 1 ohm basis. Clear? Okay. What if they were correlated? What if they were linearly dependent? In other words, let me put it this way. What if this one was B cosine 2 pi f1t? Same frequency, but it's a different what? Amplitude. Yes? Can I add the powers? I cannot add the powers. I need to add the what? I need to add the voltages. Are you following me or not? If the two sources all of this is premature, but since I was talking about the power, I just put it in there. We'll get to all of this in detail. If the two sources are correlated, then total average power. Give it to me. A plus what? Is that the same as the sum of the powers? No, there is a middle term. Did you get my point or not? Did you get my point or not? You add voltages and then what? You square and divide by 2. Do you understand why am I dividing by 2? I'm dividing by 2 because that's the averaging part. From 1/2. My cosine squared becomes what? 1/2 plus 1. Clear? Okay. Let me make one comment also before we get back to our discussion, which is what? Which is on the nonlinearity stuff. Let's see if you can follow this reasoning. Remember what I told you last time. Again, this is all premature. We'll get to it shortly. A system is said to be what? Nonlinear if it what? If it generate components, frequency components that were not available in the what? In the input signal. Okay. Now let's look at a simple model just to see what I'm talking about. This is what? This is x of t, the input, and this is what? Y of t, and this is what? Non-linear system. What is the relationship? Y of t equal to what? A sub 0 plus a sub 1, x of t, plus what? A sub 2, x square of t. Let's add another one, a sub 3, x cube of t, plus dot, 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 dot. Clear? Yeah, is this a linear system or non-linear system? Non-linear system. Clear? I stopped at the what? At the third order. Could I continue? I could continue. Okay. Now, case 1. Input is a single sinusoid. a single tone or a single sinusoid, which means what? X of t equal to what? A cosine. Can I use omega instead of 2 pi fc, or do you mind? Right? Just for simplicity, cosine omega ct, A cosine omega ct. Let's not worry about the theta right now, just to make things simple. Clear? Okay. Can I assume this one equal to 0? That's the DC component. Is this the DC component? Oh, by the way, is there a DC component here? No. Is the DC component showed up in here? I showed up in here. I reform it. Let's not worry about that, because the DC component actually will what? Will also, this is because of offset. Some offsetting there in the biasing point. There will either be another DC from where? From this term. Do you agree? Let's not worry about that. The term of interest to us is which one? Is this one. Because that's the linear portion. Did you get my point or not? Okay. X of t equal to A cosine omega ct. What is Y of t equal to? Again, ignore this. Let's not worry about it. Assume 0 just for simplicity. What do I get? I get A1, A cosine omega c t. Clear? By the way, what does A represent? A1. What does A1 represent? Assuming that the system is linear. Assuming that the system is linear, A1 is actually what? The gain. You agree with me or not? The gain. Which means what? Which means the output voltage divided by the input voltage. Clear? Okay, let's leave it like this so that you understand what I'm talking about. A2 times what? What is this? X squared, which is what? Square. So it's what? A squared over 2 plus what? A squared over 2 times cosine 4. 2 omega c t. What did I generate from this term? I generated the what? The second harmonic. Notice, by the way, if you do have a nonlinear system and the input is just a single frequency, then you are only going to get what? Harmonics. You are not going to get what? Intermodulation components. Intermodulation components is only when you do have what? 2 or more signals as the input. Did you understand or not? Yes or no? If you do have a single input, you are going to get only the harmonics. Give me the next one. Is what? A3 times what? Look how I'm going to write it. I'm going to write it x of t times x squared of t. So it's what? A3, A cosine omega ct times what? A squared over 2 plus what? Over 2 cosine. Help me. 2 omega ct. Did you get it or not? Yes? Did you lose me? Okay. Now, what is the fundamental component? At output. Give it to me. Is this, we'll look at this term. Is this fundamental? So it's what? A1, A. Is this fundamental? Is this? Why? Can you fix the screen, please? Don't move the screen. I will move the paper. Is this fundamental? This one with this one? No? Yes? Okay. Is this fundamental? So what is it? Plus A3, A cube over what? 2. Yes? Okay. I want you to see this term with this term. Cosine, cosine. What will I be generating? Cosine the sum, cosine the difference. Yes? Cosine the difference. Will it be the fundamental? What is the value? What is the amplitude? Is A3, A cube over what? Or. Did you understand why it is 4? No, I messed up. No, I did not mess up. A cube, A squared is what? A cube. Divide by 2, and then the cosine, cosine, you get another 1/2. That's this. Yes? What do I get to this sum? I get the third harmonic. Did you understand what I just said or not? Okay, let's not worry about the third harmonic. Okay, what is the gain of amplifier at fundamental? I'm still waiting. It's equal to what? A1 plus 3/4 A3A square. Why? What happened to this? Why? What happened to the AQ? Because this is a gain. I'm dividing by what? By A, which is the amplitude at the input. Yes? Did you lose me? Yes? Okay. Did the gain increase or decrease? Or does it depend on the value of A3? Depends on the value of A3. And we will see later on when we get to the design, most of the time A3 is actually what? Negative. What does that mean? As you increase, and this one is A square, which means what? As you increase the amplitude of the input, which means what? The input signal has a what? High amplitude, which translates to what? High power. Yes? What will happen to this term? Becomes what? Becomes negative. You agree with me or not? Largely negative, which means the overall gain will what? Reduce. And that will explain, I'll show you that later on, that will explain why would you get what? Get something like this. Are you following me or not? The signal actually is going to get what? Compressed. Yes or no? Yes or no? No response. Did you lose me? Okay, assuming what? This is A3 is what? Negative. I would like A3 to be equal to what? 0. If A3 is equal to 0, then what do I have? I have A1 to be what? I want A1 to be, I1 is the gain, the linear gain. Clear? Did I get intermodulation components? What are the intermodulation? Can you tell me what is IM components? Again, all of these are premature. We'll talk about them in detail. But I just brought it up because we're talking about the PAR. Intermodulation component, the structure. What is it? Let's assume that I have what? One of them is at F1. The other one is at what? F2. You understand what that means? I have a sinusoid at what? F1. I have another sinusoid at what? F2. And this is a what? Nonlinear device. N is greater than 1. Nonlinear device. Yes? Can you tell me what is the IM? How do I represent it mathematically? Plus or minus M. F1 plus or minus N of what? F2. Did you get this or not? Did you get this or not? Yeah. Do you understand what the plus or minus mean? Means what? For example, if both of them are plus, M, F1, M, what is the M and the N? The M and the N is what? Since I put plus or minus here, M and N is what? Is 1, 2, 3, and so on and so forth. Clear? Notice, by the way, if they are 0, then I'm not going to get what? Intermodulation. I'm only getting what? One of the fundamental, if you would like, F1 or F2 in there. Clear? What is the order of intermodulation? I'm still waiting. In other words, from this equation, how would you define the order of the IM? I am not sure. Did you get my question? Did you get my question? How, when you say, for example, when you say third, what does it mean? Give me an example of a third order intermodulation component. 2F1, for example, minus what? F2. Give me another example. 2F1 plus what? F2. Give me another example. 2F2 minus what? Give me another example. Are you following me or not? I want what is the, in general, when I talk about order of an intermodulation, what does it mean? It means order. Did you get it? Yes or, huh? No, sorry. Sorry, I messed up. Order. Agree? agree? Yes or no? Okay. So for example, if I say fifth order intermodulation, can you give me example? Fifth order. As for example, 4F1 minus what? F2. Another example, 3F1 plus 2F2, and so on. So, clear? We will talk about that later on. Which one is more crucial in our design? The third order the intermodulation components or the harmonics? Intermodulation components are what? More crucial. Why? Because they might be located within what? Within the band of what? Interest. I want you to see something like this. Let's assume this is F, and let's assume this is the what? This is the desired F sub C. And I have two what? Two strong what? Two strong blockers in there. Very close. Yes or no? If you pass all of these through a nonlinearity, yes, the third order intermodulation component might what? Might reside in the what? Might reside inside the what? Inside the band. Did you get this or not? And if they reside in the band, you will not be able to what? You will not be able to filter. Clear? Okay, but we'll talk about this in detail shortly. Let's not worry about it right now. Let's get back to our discussion. Is the signal getting distorted when you pass it through the nonlinearity? Is the signal getting distorted? A signal will get distorted. In addition to what? Generation of what? Generation of new frequency components. The signal will also get what? Distorted. Well, all of these factors multiplying the amplitude stuff. Clear? Okay. So we will talk about what is known as what? What is known as the harmonic distortion, what is known as IM distortion, and so on and so forth. All of these things that we will talking about it shortly. Clear? No response. Clear? Okay. So we went through all types of what? We went through all types of modulation last time. This, by the way, in the frequency bands, this column, you can read it at home. For each one, it tells you what is the most likely service to be what? To be operating in that band. For example, if you see the what? If you see the VHF, 30 to 300 megahertz, 30 to 300 megahertz, this one is what? An example of which is what? FM radio. FM radio is what? 88.1 to 108.1, which is what? Within that band. Clear? AM is within what? Within that band, and so on. So cellular could be what? Could be within that band. Clear? The UHF, and so on and so forth. Okay. The Wi-Fi, some of it is in what? In the UHF, and some of it is in the what? In the super high frequency. Clear? And I ask you, hopefully you will get it. Did you order this or not? How many of you ordered? Okay. And I hope that when you ordered it, you did not write that you are a student. Did you write that you are a student? Because if you wrote that you are a student and asking for an extra credit, they are not going to send it to you. They are in the business of making money. They want you to buy their product. They are not going to give you all of these for free just because you are taking 544. The professor is a nutcase. He is giving extra credit for a poster. Did you understand what I just said or not? I hope that you came up with some ingenuity. Tell them I'm an Arab engineer or something, consultant, whatever the case might be. Okay. These are some microwave, IEEE microwave and radar bands, satellite bands, and so on and so forth. KU bands, KA bands. Most of these are what? Are satellite bands and so on and so forth. All over, roughly to what? Roughly to 170 gigahertz and so on. We are not going to go over all of these things. Clear? Okay, good. Now, so we get into all types of modulation, AM modulation, FM modulation, PM with analog modulation, and with what? With these are all analog. Remember, by the way, I told you for analog modulation, you will not be able to tell whether it's FM or what? Whether it's PM. Clear? All what you see is something like this. Okay. Digital modulation, you will see it very clearly. And remember, in digital modulation, we have this is the what? The information or the modulating signal, and this is the carrier signal. Let me show you, as long as I'm showing you here, let me show you the IQ so that you understand what IQ stands for. This is X of T. What is this? This is C of t equal to what? A cosine theta. Question, is this constant or is it variable? Constant. Is this constant? Yes. Is this constant? Now let's assume that I'm using what? Phase modulation. What does phase modulation means? I'm going to modulate the what? The information signal, or superimpose the information signal on top of the what? On top of the carrier. Agree? What am I getting? X of t equal to what? A cosine 2 pi FCT plus what? Now it's a what? Theta of t. It's a function of what? Where this is a function of what? A function of m of t. Clear? Question, by the way. Does the amplitude actually remain constant, or there will be some variations in the amplitude as well? There will be amplitude variation in amplitude, but I'm assuming that the carrier frequency is what? It's so fast that it will go from one signaling point to another signal point very quickly. Clear? So, and what can you do? This is what? A cosine theta t cosine 2 pi FCT minus A sine theta t is sine 2 pi FCT. Yes or no? This is what? I of t, the information on the I channel. Yes or no? This is the information in the what? Q channel. Cannot hear you. And so what do I have? This is the I of t multiplied by what? Cosine 2 pi FCT. Where is this coming from? That's coming from a local oscillator at the transmitter side. At the transmitter side, local oscillator. And then what do I have? What does this mean? 90-degree phase shift. By the way, designing this later on, we'll see, it's not that hard. Why? Because I am introducing a 90-degree phase shift for a what? Single frequency only. Did you understand what I just said or not? I am not introducing a 90-degree phase shift for what? For a range of what? A range of frequencies. Only for what? For one frequency. What am I getting here? I'm getting the sine 2 pi FCT, and I'm going to multiply it with what? Q of t. Are you following me or not? And then what do? I add it together to get X of t. Clear? Clear? Now, we are not ready yet. We'll get to it shortly. We are not ready yet. Why am I splitting this into an IQ? That I need to show it to you. Are you following me or not? That I need to show it to you. Why are we splitting this into IQ? For time being, just accept it. I just showed it to you. Detail is coming attraction. Coming attraction means what? When you go to a movie, you see what? Coming attraction is what? Next week or something. So this is the same thing in here. Okay. Now, the digital, again, as I told you, the binary modulation, or when you hear the word binary, what does it mean? One bit goes into the modem, one signal goes out, which means what? RB, which is the what? The bit rate is equal to what? RS, which is the what? The signaling rate. Units signaling rate, both. And what is the relationship between them? RB equal to what? K, RS. For binary, what is K? K is equal to 1. One bit goes in, a signal goes out. Clear? Okay. RB equal to what? KRS. This is, again, binary phase shifting. The phase is changing, but it's the same, still binary. QPSK, we did this last time quickly. QPSK, what do we have? K is equal to what? 2, which means every what? Every 2 bits goes in, one signal goes out. How many phases do I have? 4 phases. These are the 4 phases. Answer me the following question. This is what? 0, 0, 0, 1, 1, 1, 1, 0. Whereas in the previous one, this is the PBSK. The phases are what? 0 and pi, or 0, 0, 1. This is what? 180 degree. This is 0 degree. Yes or no? Okay, I want you to see this. Can I regard the QPSK as two perpendicular PBSK? I can regard it as what? Two perpendicular PBSK. We will see later on when we get to the details of this, we will see that the bit error rate of this will be what? Will be the same as the bit error rate of this. However, the symbol error rate, the symbol consists of how many bits? 2 bits. The symbol error rate in here is worse than the what? Than the symbol error rate in here. By the way, in here, the symbol error rate and the bit error rate are what? Are the same, because the bit is the symbol. Clear? Why is the symbol error rate here will not be as good as this one? Because the faces got what? Closer. Yes or no? How about 8 PSK? Those points, by the way, are these points around a circle? They are around the circle. Yes? Or what about 8 PSK? Are they still going to be around the circle? But are the faces getting closer? Yeah, the faces are getting closer, which means what? The symbol error rate will be what? Will be worse. Clear? Now, in this case, the bit error rate also will be what? Worse. Why? Because each symbol is representing how many bits? 3 bits. So you could have what? When I tell you a symbol is in error, you could have what? You could have 1 bit in error, or you could have what? 2 bits in error, or you could have what? All 3 bits are in error. We'll talk about that later on. QAM is the quadrature amplitude modulation. Again, once you get into these types of modulation, the par will be high or low. The par, the peak power to the average power ratio. Will it be high or low? It will be relatively high. Clear? Will be relatively high. Why? It's because the amplitude is what? Amplitude is changing. Clear? No response. Clear? Okay, good. Now, in this case, it's 8 QAM, which means what? It means I have 2 amplitude and 4 phases for each amplitude. Why modulate? All of this we did last time. Why do we modulate? We modulate is because what? Because the size of the what? The size of the antenna, to become an efficient antenna, the size of an antenna needs to be a fraction of what? Of the wavelength. So if you do not modulate, the wavelength will be what? High or low? If you do not modulate, which means what? Baseband, the frequencies are what? Low, which means what is the wavelength? So the low frequencies corresponds to what? A higher wavelength, which means the size of the antenna will become what? Not practical. Doesn't work that way. Clear? Clear? Okay. How many of you have direct TV or direct or dish network at home? Anybody? Anybody? How big is the antenna? Small antenna. Are you following or not? Why? Because you are transmitting at what? At the KU or the KA band to the satellite. Clear? The higher the frequency, the antenna becomes what? Smaller and smaller. It becomes like, that's why they call it a dish stuff. Oh, another reason for your modulation is what? To allow for simultaneous transmission. Otherwise, without modulation, you are not going to be able to support what? Multiple AM broadcasters or FM broadcasters. All of them are transmitting using what? Baseband. If you are not going to modulate, are they going to be overlapped? And forget about the antenna size. Let's assume the antenna size is not the issue. Yes? Can you transmit them simultaneously? Why? Do they overlap? They overlap in frequency. They overlap in what? In time. Is there any way you can separate them at the receiver? You are not going to be able to separate them at the receiver. With modulation, what you are going to do? You are going to what? You are going to shift the spectrum to different what? Different frequency regions. Clear? So they don't overlap, and you are able to separate them at the receiving end. Keep in mind, when you separate them at the receiving end, you need to what? You need to demodulate to bring it back to what? Baseband. Otherwise, you will not be able to what? You will not be able to hear it. Other benefits of modulation: minimizing the effect of interferences. Some bands are what? More prone to what? Interfering. Why? Because there are other devices operating nearby in the vicinity. Clear? More other bands are quieter. So with modulation, you can what? You can shift the spectrum into a region in which you don't have that much what? Interference. And at the end, you can what? Shift it back. Clear? Shift it back. This is what to place the signal in a frequency band where it's easier to design the amplifier, the filters, and so on and so forth. The choice, when you choose a modulation technique, you need to look at what? You need to look at the available power. If the available power is not much, which means what? It means, for example, in your mobile devices, these operates using what? Batteries. You don't want to use modulation technique that are what? That are power intensive. Power intensive means what? Requires a lot of power. You follow me or not? You need to use what is known as what? Power efficient modulation technique. On the other side, you use, for example, if the bandwidth is abundance, for example, over a satellite link, then you use what? You use bandwidth efficient modulation technique so that you can use the bandwidth efficiently. I will show you that in just a second. You need to make sure when you choose a modulation technique, you want to use that the power spectral density is what? Confined within the emission mask that was set by the FCC, cannot exceed it. Clear? Okay, you need to make sure to minimize the effect of what? ACI. ACI stands for what? Adjacent channel interference. Notice, by the way, when we talk about adjacent channel interference, we are talking about what? Other channels within the what? The desired band. We are not talking about what? Out of band. Out of band usually is going to be what? Filtered out with the band select filter at the front end of your receiver. At the front of your receiver, you are going to get rid of any out of band frequencies. What remain is what? Is the in-band frequencies. That's the whole issue. Okay, you need to what? To make those side lobes what? Roll off very quickly. We will see that later on. You want also to come up with a what? Bit error performance. Bit error performance actually depends on the application. Some application can tolerate relatively what? Modest bit error rate. It's okay, for example, for the voice, but for data, it cannot tolerate what? Excessive delays. Clear? Sorry, it cannot tolerate excessive losses. Clear? Or errors. Envelope properties have to do with what? With the design of your power amplifier. You would like to use the power amplifier as efficiently as possible, which means what? Operating at what region? Near the saturation region, very near to the saturation region, or in the saturation region, before what? Before it gets compressed. Yes? Okay, but on the other hand, you need to look at your modulation scheme. If your modulation scheme is employing a if it is a non-constant envelope, then the saturation, as I showed you a moment ago, will result in what? In compressing of the signals. Clear? Compressing of the signals. Okay. Why digital modulation? In other words, remember I told you the modulating signal could be analog or it could be what? Digital. Why digital? Everything better in what? In digital. One of them, the first or most important, is that you can do integration of services. You don't have a system for voice, a system for data, a system for voice, for video. All of them, when you digitize them, all of them are what? Zeros and ones. Do you agree? Do you agree? Whether they were voice or whether they were data, they would look like what? Zeros and ones. That's what it means by what? Integration of services, increasing of information capacity. We'll talk about that shortly. Better quality. Why is it better quality? Better quality because we are dealing with how many levels? The two levels, zeros and what? Ones. Whereas in the case of analog, how many levels can the analog signal take? Infinitely uncountable number of values. So in terms of what? In terms of compression, by the way, all of these baseband operation, compression, encryption, much more or much easier to use using what? Digital domain rather than the analog domain. Clear? Okay, good. Now, in duplexing, I'm not sure if we did this last time or not, but let's do it right now. Don't confuse the duplexing with the what? With the modulation. These are two different issues. Duplexing means what? It's the direction of transmission. We have what is known as TDD versus what? FDD. TDD stands for what? Time division duplexing. FDD stands for what? Frequency division duplexing. In a frequency division duplexing, this is our transceiver. This is the transmitter, diplexer here, or sometimes they call duplexer. This is the receiver. You are transmitting and receiving. By the way, using the same antenna. But when you are using FDD, what does it mean? It means that you use a frequency, two channels. You need two channels. One on the uplink and the other one on the what? On the downlink. Why not the same frequency? Oh, the same frequency means what? The uplink and the downlink will what? Will interfere with each other. Clear? Okay, sometimes you will see in satellite, for example, you will see this notation, 12/14 gay. What does it mean to 12/14? Means, say that again? One for the uplink, one for the what? One for the downlink. You don't want to put it the same way, otherwise the uplink and the downlink will what? Interfere with each other. Clear? So when you see like this, or 5/6, something like that, you know that it is what? One on the uplink, one on the downlink. Clear? An example, by the way, on the 2G, I think I showed you this last time. It's what is the second generation, the mobile receiving, which means what on the downlink? It's anywhere between what? 869 to what? 894, 25 megahertz. This is on the what? On the uplink. Clear? This on the uplink. Now on the antenna you have this, but the diplexer will what? Will separate this one here, this one here. Clear? Okay. We'll talk about that later on. Some devices, some wireless devices, for example, majority of them are cordless. Cordless uses what? Time division duplexing. Time division duplexing. In time division duplexing, you are using the same frequency, but different what? Different times. Are you following me on that? Different times. So for example, if this is a frame, this in time, a one-time slot for the uplink. Uplink means what? The mobile to the base. On the next time slot is what? Downlink to what? Uplink. Sorry, from the base to the what? To the mobile. Mobile to base, base to mobile. Mobile to base, base to mobile. And in this case, instead of a duplexer, because it's the same frequency, we use a what? An RF switch. We'll see later on how we design that switch electronically. Clear? Switches between what? When you are transmitting and when you are receiving. Clear? Now, answer me the following question. Premature question, but answer to me anyway. In this case here, suppose I have two base stations. Two base stations. Nearby, base stations. Okay. Will a base station interfere with another base station? I'm not sure, did you get my question? Or will a mobile interfere with a mobile? In FDD, I'm not sure you are getting my question. Are you getting my question? No. You are not getting my question. Okay, in FDD. By the way, this is the hexagonal. It's easier to sketch it as a circle, just for simplicity. Okay, this is a mobile. This is a base station. This is another base station. This is another mobile. This is another mobile, all over the place. Can I have MS to MS interference? Or BS interference? Yes or no? In FDD, I'm still waiting. Can we have MS to MS? Why? In other words, it's different range of frequencies. This MS, when he is transmitting, he is using a frequency from which band? From the uplink. When this one is receiving, he is receiving from what? On a channel on what? On the downlink, which is not the same as the uplink. Which means what? This one is not going to interfere with this one. Did you get my point or not? And similar between what? BS and BS. Did you lose me? Yes.
What if all three mobile stations are trained? They all use the same.
I didn't get that.
But you're saying that if one mobile station...
No, this one, they cannot use the same frequency. There must be a what? A spatial separation. But they are not going to be what? Interfering with each other. Why? Because in FDD, when... I'm not sure, did you get this? One more time. In FDD, in frequency division duplexing, a mobile transmit from which range? I am talking about what? A mobile transmitting, interfering with who? With a mobile in the vicinity. In other words, the mobile, see, this mobile is supposed to receive the signal from who? From the base station. Is it possible that the signal that is transmitted by this mobile interfere with the receiver of this mobile? Did you get my point or not? We are not talking about what? Transmitters. We are talking about transmitter of one mobile interfering with a what? the receiver of an adjacent mobile. Clear? Yes or no? Okay. In TDD, is that possible? In TDD. So this one, not possible. Did you get this or not? Yes. This one is not possible. In what? So which interference is possible? Oh, sorry. Sorry. I messed up. I know when I mess up, everybody jumps all over me. I try to choke me. But that's fine. It means that you are awake. Answer me. Which interference do we worry about here in FDD? In FDD, which interference? In other words, will there be interference? Where? From where? From a BS, another base station, interfering with the what? With the desired mobile. You lost me here. Did you lose me?
You mean the co-channel?
No, not necessarily the co-channel. Adjacent channel. Does not have to be the co-channel. But I'm strictly talking about the co-channel. But it does not have to be co-channel. Adjacent channel. What I'm trying to tell you is the following. If this base station is a transmitting, let's assume this is the desired base, this is the desired mobile. If this base, let's assume this is a co-channel base, is it possible that then when this one is a transmitting, it will interfere with the reception of this mobile? Reception of who? Of the desired signal. Especially if this happens to be what? Farther away from here, and there is another what? Another transmitter in the vicinity of this. Did you get this or not? So you have what? BS to MS interference, or what? MS to BS interference. Did you lose me? Did you lose me? Okay, good. In TDD, do I have MS? In TDD. Why? Because they are transmitting using the same what? Using the same frequency. Are you following or not? Sorry, you are transmitting and receiving at the same what? At the same frequency. The time slot will change. So in TDD, we shall have MS to MS and BS to BS interference. One of the mini projects, I call them mini projects because they are extra credit that will I assign. I will ask you to what? I will ask you to simulate the interference. I will ask you to simulate the interference between what? The MS and BS. All of this, by the way, is supposed to be interference. It's supposed to be in 535, EE 535. But I was told that in EE 535 there is no project. Is that true or not? Which I cannot understand that, but I don't care. I only care about my kids. I don't care about other people's kids. Clear? Okay, good. Now, let's continue. And again, as I told you last time, the communication channel is a what? It's a shared channel. Always remember the rule of thumb. Whether it's what? Whether it's Wi-Fi or whether it's cellular, whenever the channel is shared, whenever the medium is shared, we need to have what? Medium access control procedures, a MAC procedures, or multiple access procedures. You cannot just say what? Yeah, go and let's play by the rules of the jungle. We cannot do that. We have to play by the rules. Clear? Okay. So whenever we do have a channel, remember, by the way, we could have multiple transmitters, multiple receivers, and so on and so forth. Interference will all over the place. And again, we did this last time. I don't want to repeat this. By the way, this will be discussed in 535. The propagation channel and stuff, he will discuss this. But I'm not sure if he will discuss interference issues, which is very important, by the way. Remember, by the way, one more time, if the FCC assigns a license band to a single operator, naming the operator, for example, Verizon, we don't worry about what? Interference, because they are not going to interfere with what? With themselves. This is the same company. You follow me or not? We don't worry about other users. Clear? Okay. Now, multiplexing or sharing the channel. Let's look at some techniques that are going to be used. The first one is called what? Frequency division, multiple access. What do? I take the band and I divide it into what? I divide it into non-overlapping frequency channels. Clear? Non-overlapping frequency channels. And I assign to each channel to what? To a single user. Clear? Same idea, by the way, in a frequency hopping. But in frequency hopping, instead of assigning a single channel for a user, I will let the user hop. Hop means what? Jump from one frequency to another frequency, each according to a certain what? Sequence. Yes or no? Now, question. Is it possible that there comes a time where the there in the sequence, two frequencies will collide? Yes. It is possible. But the hope is that this one will only occur for a what? Short period of time, such that what? The data that is lost is minimal. Did you get my point or not? Now, you might say, why are we jumping from one frequency to another frequency? You will study in 535 and even in this course later on that the available bandwidth, some frequencies might what? Suffer from severe fading. You are trying to get out of the fade region and then what? Go back until the fade goes away. You have to understand that the fading is going to be what? Is going to be changing based on the relative motion of the mobile and the base. Clear? Clear? Okay, good. Now, keep in mind, by the way, if you do have fixed wireless access, what does fixed mean? You are not moving. And if some frequencies happens to be what? In a fading region, that fading region might remain. I'm not sure, did you get my point? Did you get my point or not? The mobile is not moving. And if a frequency happens to be in deep fade, it might be in deep fade for a what? Prolonged period of time, resulting in loss of your what? Loss of your data. Did you get this or not? But that you will study it in 535. He needs to do something. I cannot do all the work. He needs to do something. Clear? What is this is, by the way, the 1G, the first generation. It was based on this. Question, what is the problem with this? The problem with this is that sooner or later you are going to run out of what? Out of frequencies. Clear? By the way, that's the whole idea about the cognitive radio, is that even though, you see, these frequencies are what? Are going to be pre-allocated to you for the duration of the call. During the call, if you are not sending anything, this channel is what? Cannot be used by some other person. Not sure, did you get my point? Did you get my point? It cannot be used because it's what? Pre-assigned to you. Clear? And remember, by the way, if you are using FDD, frequency division duplexing, for every call, you are going to get what? Two channels, one on the uplink and one on the downlink. Clear? Okay. Time division multiple access. What did I do? What did I do? This, by the way, this one is the what? Is the frequency. This is the what? The time. Using the same frequency, I'm going to divide the usage of that frequency into what? Time slot. And I going to assign the time slots to the, who's I? I keep saying I. Who's I? The base station. The base station is going to what? All mobile stations are going to be synchronized. He will what? The base station will tell them what? Synchronize the clocks according to what? Time access slots. The first time slot will be what? Yours. Second is. Third is. Fourth is. How come all males? I don't have females in the class. Okay, all the females are sitting in the back. Clear? Are you following me or not? Now, I want you to understand one thing here. So this is what I have now. This is the time, and I'm dividing it into what? Into time slot. Question. During that time slot, who is sending? Who is sending the data? Mobile number what? Mobile number one. Let's call it what? User number one. Now, during that time, are the other users stop talking? They are not talking? So what happens? They are actually talking, but it is what? Being buffered in your what? In your mobile unit, in your wireless unit. It's buffered. Until what? Until your time slot comes, the mobile unit will what? Burst it at a much higher rate than the rate you are what? Generating it. Who's you? Who's you when I say generating? Who's you? The user. Are you following me or you are losing me? It gives the impression that you are all making the calls at the same time. But are they at the same time or actually interleaved in time? Interleaved in time, but because the transmission is what? Burst in nature. Let's assume you are generating the traffic at a rate of what? Just an example. At a rate of 8 kilobits per second. That's compressed voice, by the way. One of the GSM. GSM stands for what? The global system for mobile communication. You generate, or at 13 kilobits per second, the old version at 13 kilobits per second. You are generating at a rate of what? 13 kilobits per second. When you burst it, you will be bursting it at a rate of what? Just to put the figures there, at a rate of 270 kilobits per second. Higher or lower? Much higher? To you, it seems that you are what? Continuously transmitting. But are you continuously transmitting? No, you are bursting. Are you continuously speaking? You are continuously speaking, but your mobile unit will what? Like this. Burst in fashion. Clear? Clear? In GSM, every frequency is subdivided into 8 time slots, which means what? 8 users can use what? A single frequency. Every user can use the same frequency, but at different time. Now, you might say, Professor, but if I take 13K and you multiply it by 8, you will end up with what? 13 times 8, 13, 13 times 8, 13, 104 kilobits per second. How come you said what? 20 kilobits per second. You need to add what? You need to add headers. You need to add the error correcting codes to your transmission. Are you following me on now? So when we say 270 kilobits per second is the burst data, this is not the data, the raw data that you are what generating. This is in additional to what? All types of what? Overhead. Good or bad? Good. Why? Because in GSM, for example, just an example, you have increased the capacity by how much? By 8 without using extra bandwidth. Do you understand that or not? Without using extra bandwidth, you have increased what? You have increased the number of users. Clear? But the problem with this is that you need what? You need a precise synchronization. Otherwise, if those time slots are not properly synchronized with the what? With each mobile unit, you are going to get what? You are going to get interference. In other words, somebody will be transmitting bursting during the time slot that are actually what? Allocated to you. Somebody else will be sending, which means what? They will interfere with you. Why will they interfere with you? They will interfere with you because you are using the same what? Using the same frequency and you are transmitting at the same time. Clear? Okay. Now, most of the time, again, the TDMA is used in conjunction with the what? FDMA. By the way, FDMA is what? Has to be there. Do you understand that or not? In other words, the band has to be divided into what? Into several channels. You cannot say what? I'm going to use the entire band as just what? One channel. Did you understand what I just said or not? You need to divide the band into a channel. If you run out of one channel, in other words, let's assume that one channel is subdivided into what? Into 8 users, time slot. What is next? You use another channel and you divide it into what? 8 time slots. So you will get something like this. It looks like, what is the game the kids like to put this? Huh? Lego. Lego. It looks like Legos. It's a joke. We already know that Arab engineers have no sense of humor or whatsoever, or at least students of 544. No sense of humor whatsoever. The third type is called what? Code division multiple access. In this case, the users are allowed to be transmitted at the same time, at the same frequency, but using different what? Different codes. Now, you might say, Professor, if they transmit at the same time and the same frequency, wouldn't they interfere with each other? They would. They would overlap with each other, both in time and what? Frequency. But because the codes supposedly are what? Orthogonal, the receiver will be able to what? Will be able to separate one code from what? Another code. Assuming, of course, assuming that the codes remains orthogonal at what? At the receiver side. In CDMA, you are going to use a what? A much wider bandwidth than the what? Than the TDMA and the what? FDMA, using direct sequences and so on and so forth. Clear? Using a larger bandwidth, we will see later on, and in 535 is a method of what? Method of overcoming some kind of what? Some types of fading. The larger the bandwidth is, the delay spread will become what? Smaller and smaller, which means what? Also reduce the intersymbol interference. We'll talk about that later on. Clear? And of course, the last one is the what? Is the spatial separation, spatial division multiplexes, where you are going to operate what? Where you are going to reuse the frequencies, provided that they are what? provided they are separated enough in physically, in space. Clear? Okay. In this case here, by the way, anybody can tell me what is the reuse factor? The reuse factor in this case is what? This going here? Here. Are you following on now? So you skip every what? Excuse me, you skip every other one. Clear? You skip every other one. Is it possible that you reuse the frequencies in every cell? In Cdma, you can do that. In Cdma, you can do that, provided that the codes are what? Are orthogonal. Notice, by the way, choosing codes or inventing codes are easier than what? Getting bands from the FCC. FCC does not deal with what? Codes. The FCC is in the business of what? Coming up with codes for you. You need to design codes yourself. Clear? The thing that is precious is the what? Is the spectrum that is the precious thing. It's not the codes. Clear? Okay. But keep in mind Cdma, by the way, for the 3G and the 4G, the Cdma was the adopted technology of use. Different types, they called it at the beginning Cdma 1, they called what? Cdma 2000, then they called what? Wideband Cdma, and so on and so forth. All types, some form of Cdma sometime or another. The OFDM, the orthogonal frequency division multiplexing, you are going to take what? You are going to take your high data rate and split it into what? Multiple streams of lower rate. Remember, by the way, listen to me. The higher the data rate, did I show you this last time? The higher the data rate, the spectral becomes what? The Fourier transport or the spectral density will become wider or narrower? Wider. Are you following me or not? Wider. And if the channel does not have the right bandwidth, what does it mean? The bandwidth of the what? Of the channel is less than the bandwidth of what? Of the signal, resulting in what? ISI, intersymbol interference. Yes or no? I will show you that later on in detail. But what I'm trying to tell you, in OFDM, you take the high speed or the high rate and you divide it into what? Multiple lower rates. Multiple lower rates, and you modulate carriers that are orthogonal with each lower rate data. And then you what? You combine them. Clear? But I will show you that later on. And I'm not sure if this is covered in 535. I think it's covered in 635. However, I cannot be sure that you are still alive when 635 comes. You might have graduated already. So I will give you overview of OFDM. I must give you overview of OFDM later when we get to the modulation technique. Clear? Clear? Now, this is called what? Cellular planning. And again, as I told you, when you design your RF system, at the beginning, you worry about what? You worry about coverage, and then you worry about what? You worry about capacity. Of course, every provider wants to increase capacity because increasing the capacity translate to what? More money. Show me the money. Show me the money, like in the movie. Are you following me or not? Clear? Okay. Now, to increase the capacity, you need to what? Reuse the frequencies sooner. By sooner means what? Closer rather than what? Farther. So you reuse the band by defining what? By dividing the cell into what? Into smaller cells. Right now they do have what is known as what? Femto cells, which are what? Very small in size. Clear? In a rural environment, you can afford using what? A larger cell size, because the antenna will be also what? Higher. The base station antenna will be higher to cover what? A larger area. But for the dense urban or the suburban areas, you cannot afford to make your antenna what? Higher, because you are going to cause interference to what? Other cells down the line. Did you get this or not? Okay, good. We will talk about that later on. Now, when you talk about efficiency, you need to understand one thing here, three things. The first of all, bandwidth efficiency. This is very important. I need you to understand it very clearly. Bandwidth efficiency, units, anybody, say something, breathe. Bandwidth efficiency measured in what? Anybody, bits per second per what? Hertz. Bits per second per hertz, which means what? In a given bandwidth, In a given bandwidth, how much data rate can you what? Support. The higher this one is, what do we say? This modulation technique is what? Bandwidth efficient, which means what? You are cramming more data. So what is the equation here? RB is the bit rate divided by what? W. W is the what? The bandwidth. Huh? How much W are this? W, wrong W. Clear? Clear? Okay. QPSK, QAM is what? Is a family of modulation techniques that are what? Bandwidth efficient. Unlike what? Unlike MSK or GMSK or any frequency shifting mode. Frequency shifting mode are not what? Bandwidth efficient. The bandwidth efficient, they what? The higher, this is a ratio. For example, when you say 2 to 1, what does it mean? In a given bandwidth, when 1 hertz, you are supporting what? 2 bits per second. Clear? In a QPSK or QAM, this is what? This is high. Clear? More than 1. Okay. Power efficient. Please give me 1 minute. 1 minute. What did he say?
1 minute.
Oh, yes. The power efficiency is what? Is uses minimum EB over N0. This one we will call it EBNO. Next time I will show you EBNO. EBNO means what? EB over N0 to achieve the same BR. BR stands for what? Bit error rate. Clear? Bit error rate. So for example, if you look at the, you have seen all of this. Have you seen these diagrams? Okay, the Niagara Falls or something. This is EB over N0. And this is the bit error rate. Tell me which one is more power efficient. This one or this one? This one. Why? Because it needs that much, whereas this one needs what? That much. Did you get this or not? Which one to choose depends on which is available to you. If the power is what? Little that's available to you, you need what? Power efficient modulation technique. You don't want to spend too much power. Clear? If the bandwidth is what? Large available to you, you want to use it what? Efficiently as possible. Clear? You use what? Power efficient technique. And then cost effectiveness or cost efficiency, of course. You don't want to design what? You don't want to design systems that cost a lot. Clear? But we'll continue this next time. I was still not able to finish this set of charts. I mean, what's the matter with you?